Hello students, welcome to Sourabh classes. Uh, we are discussing on mechanism of substitution reaction, and now our topic is uh, nucleophilic aromatic substitution reaction. Now, in general, aromatic compounds does not undergo substitution, nucleophilic substitution, because due to the fact that this aromatic ring is electronically rich and high electron density in the aromatic ring, which repels the nucleophile. Either it is negatively charged or this molecule having lone pair of electrons, there is a repulsion between them. So it is not energetically favorable process for nucleophile to attack this ring. That is the number one point. And number 2 point is that the removal of this H minus, which is also not favorable because it is a strong base. And for removal or for the leaving group should be a weak base. For leaving group, that should be a weak base for substitution reaction So what we see here is that this leaving group is not favorable, and also the high electron density in the ring that does not allow this nucleophile to attack in the aromatic ring. So aromatic halides are not usually replaced by the nucleophile. But if there is an electron withdrawing group such as NO2 group are present in the ring, in that case the ring become electron density is reduced in the ring due to the electron withdrawing effect of this nitro group. In that case, the nucleophile can attack at the benzene tail. Such if the example is like that, if we add nitro group in para and ortho position, we can find that in that case nucleophile can attack at this center. Suppose if we have a nucleophile Y, then it can attack here, and this process is a slow process, and we get the product like this one. Then this negative charge is resonating with this pi electron, and we are getting this resonating structure. this one. Again this sorry, this is not like this. This is the negative charge here, and this negative charge, and we have this negative charge is shifting here, and this is shifting here. And the next step is like this. The next step is Y and X, and finally this X is removed, and finally this X is removed, minus X minus, and we are getting the nucleophilic substituted product, this one. Y NO2. So the presence of NO2 only enhance the possibility of this nucleophilic substitution by withdrawing the pi electron from the ring and creating electron deficiency in the ring. There are other examples there where nucleophilic substitution is taking place in aromatic ring, that is by that is through benzyne intermediate. And this benzyne intermediate, it is formed like if we have this type of halobenzene, and it is bearing the hydrogen, and when it is treated with amide NH2 minus in liquid ammonia, we are getting this compound, this amide is abstracting this proton, and this anion is generated, and this on release this Cl minus, and we are getting the benzyne intermediate, now this benzyne intermediate, here this ammonia is attacked here. Now this attacked by the ammonia can be take place either in this side or in this side. Both sides, either from this end or in this end, this ammonia can attack. So we can get two products where one is NH2, that is NH3 minus H plus, and another product is So what we see, if we keep this carbon as radioactive, then it will find that in one product this NH2 group is attached to this radioactive carbon, and another case it is attached to adjacent carbon to the radioactive carbon. So this indicates that this type of intermediate benzene, this is the benzene intermediate, this is the benzene intermediate, benzene intermediate is formed. So this is another type of nucleophilic substitution that takes place in case of aromatic compound. Now we are coming to aromatic electrophilic substitution. Now this aromatic electrophilic substitution, this is initiated by the electrophile, that is either an electron deficient species like a positive species, or a molecule having electron deficiency. Suppose if we take E plus, it is an electrophile, and then the reaction proceeds in the following mechanism. This proceeds in the following way. One hydrogen is removed and the electrophile is produced. Electrophile is replaced here. The one hydrogen is replaced by this electrophile. Now the proceeding steps here is, for the mechanism, is number one, the generation of electrophile. Number two is the attack of electrophile, to aromatic or to pi electron system, electron system. And number three is the removal of proton by base. So these are the three these are the three steps involved in the aromatic electrophilic substitution. Now if we look into the mechanism, this mechanism as follows. E plus, this polarizes these pi bond, and we are getting this polarizes this pi bond, and we are getting this compound, this species. This is plus, and this is hydrogen, and this is here is 1 2, and this positive, this cation is further resonates. This pi bond is shifted here, and positive charge is here, and from here again it is this one, and here is one hydrogen and one E, and from here this hydrogen is removed, and again aromaticity is regained. So this step is very fast and aromaticity is regained by the compound. So in this species this aromaticity is lost, which is further regained by elimination of this proton. And so these are the canonical form, these are the resonating structure of this electrophile which is produced in the intermediate of this species, which is formed by attack of this electrophile, and finally we are getting this substituted proton. Now for example we can see for number 1 here nitration of benzene ring. In this case this compound HONO2, this is reacting with H2SO4 and it is giving us this NO2 plus H3O plus HSO4 minus. Now this compound, this NO2 plus, this step is the generation of electrophile. Now this electrophile is generated here, and this electrophile attacks the benzene ring in this way. NO2 plus, this attack the benzene ring, and we are getting H, and we have a positive charge there, suppose, and this is this step is the second step where this attack is taking place. This is the step 1, suppose, and this is the step 2 where electrophilic attack taking place, and from here this proton is eliminated, and then we are getting this nitrobenzene. So this is the step 3. This is the step 3. So what we see is that this is the step 1 where this this is the step 1 where electrophile is generated. The step 2 is the attack of the electrophile to the ring, pi electron system or aromatic ring, and step 3 is the removal of this H plus, and finally we are getting the product nitrobenzene. Similarly, similar type of reaction is also observed in case of Friedel-Crafts reaction, where alkylation or acylation to benzene ring is taking place through formation of this electrophile. So our next discussion is Friedel-Crafts reaction. Friedel-Crafts reaction here. This first step of this reaction is the formation of this carbocation, where this alkyl halide, suppose CH3Cl, this reacts with anhydrous AlCl3 to produce CH3 plus plus AlCl4 minus, and this ACH3 plus in the next step attack the benzene ring, and we are getting this product, CH3. This is this is here we have CH3H, and here we have positive charge, suppose. And next step is the elimination of this H plus, and we are getting this product. This is toluene. Now the thing is that this hydrogen is removed here, and this is the third step. This is the third step. This is the second step, and this is the first step. That is formation of carbocation, then attack of the electrophile or carbocation to the benzene ring, and then removal of this proton. This is the minus H plus. Yeah. So we can say here that this reaction is proceed through electrophilic substitution by formation of this electrophile. Similarly, in case of acylation, physical acylation, we can use this CH3 COCl and anhydrous AlCl3, and this gives us CH3CO plus AlCl4 minus. Now this CH3CO, this is attacking here, and this is attacking this CH3CO, that is the acetyl carbocation which is produced. This is attacking at the ring, and we are getting this product, this intermediate product, HCOCH3, and this is positive, and in the next step this hydrogen is removed, and we are getting this product, and we are getting this product minus H plus. COCH3. This compound is known as acetophenol. This is acetophenol. Acetophenol. So here we are also writing, this is the first step, step 1, where electrophile is generated. Next step is the attack of the electrophile, and the third step is the removal of this cation, so that aromaticity is regained. So in this way, this electrophilic substitution proceeds. This is also Friedrich reaction, where this electrophile attacks at the aromatic ring, and followed by removal of proton, we give the product. And here these intermediates are very much unstable, so we cannot identify or separate these intermediates because their shelf life is very short. So all about this Friedrich reaction and aromatic electrophilic substitution. Thank you for viewing this video.